Okay, our next topic is systems of linear equations. I'm going to define what I mean by that in a second. If we had an extra 10 hours for this course, I could tell you all about applications of systems of linear equations. It's one of the most useful things in applications of mathematics across all topics and subjects and fields that use mathematics. But we're really only going to deal with basic math. This is just an algebra course. So here's a linear equation. A linear equation looks like this. A1 x1 plus a2 x2 plus dot 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 plus an xn equals b. So the ai's, these are called the coefficients. So these are the coefficients. Coefficients. Oops. And the x's, and these are not powers. It's not a polynomial. Okay, these are just different x's, are called the unknowns, often called the variables. So the x's are the unknowns. Okay, or variables. Or unknown variables. Okay, and b is sometimes called either the free coefficient or the constant or something like that. Okay, and by the way, this can be written in short using sigma notation. Sum I equals 1 to n, ai xi equals b. This is sigma notation for this longer expression. Do you agree? Okay, here are some examples. So examples. 3x plus 4y equals 7. Often when we do examples, we won't call all the x's by x1, x2, x3, etc. If there are just a few of them, sometimes we just use different letters for them. So this is a linear equation with two unknowns, right? And geometrically, I hope you know this equation describes a line in the plane, okay, as a function, right? And that's why it's called a linear equation. That's the basic motivation for the name, okay? So this is the equation of a line in the plane. What I'm not sure you know, so here's another example. So 2x plus 3y plus 5z equals 10. So here's a linear equation with three unknowns. Do you know what this describes geometrically? Have you seen it before? No, it's going to be a plane in 3D space. Okay, so if you want to describe a plane, where am I? A plane in three-dimensional space, that's going to be the equation. Okay, so if you haven't seen this before, you're going to encounter this when you discuss the basic geometry underlying multivariable calculus. In the Technion, it's Calc 2, but I'm just going to mention it so you know, and we're not going to use the geometric aspects of these equations. For us, they're just equations. Okay, so this is the equation of a plane in three-dimensional space, often denoted as R3. Okay. X squared plus y equals 5. This is not a linear equation because there's an x squared. Okay? Or x minus xy equals 4. Not a linear equation because there's a term xy here. Okay, so both of these not linear. And therefore, we're not going to be dealing with these at the moment. Okay, only linear equations. Okay, what is a solution to a linear equation? So we're going to call it a solution vector because we're going to write it as a vector, and you'll see why shortly. So a solution vector is something of the form x1, x2, dot, 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 xn. A vector is just, this is a row vector, so it's a 1 by n matrix, right? So this is a solution vector, is a vector like this, such that if we plug in these x's into the equation, we get equality. Okay, such that if we substitute, this word always confuses me. Substitute the x's, the xi's, into the equation, they solve it, or they satisfy it. Okay, so for example, 1, -1, 0, 2 is a solution vector of the linear equation 2x1 minus x2 plus 3x3 minus 4x4 equals -5. Do you agree? So you have to plug in the values for the x's and see if you indeed get an equality, if they satisfy it. So this is 2 minus 1, so it's 3 plus nothing, because we're plugging in a 0, so it's 3 minus 8, right? 3 minus 8 is -5. It's indeed a solution. Good, everybody? So is 0, 5, 0, 0. This is also a solution of this equation. It's even more straightforward to verify. Do you agree? Okay, so that's the notion of a solution, or a solution vector of a linear equation. Another example, before we define it formally, x minus y equals 3, and 2x plus y equals 9. This is a system of two equations, two linear equations, with two unknowns. Okay? The unknowns are x and y, and you can see that there are two linear equations, and the way to denote it is this squiggly brackets on the left. Okay? So this is a system of two equations. Let's do a more interesting example of a system. So here's another example. So there are going to be here three equations with four unknowns. And the equations are going to be the following. x1 plus 2x2 plus 3x3 plus 4x4 equals 13. 2x1 minus x2 plus x3, and there's going to be no x4, but I'm going to write it so they're all in the same columns. You'll see why in a minute. So I'm just leaving a blank space here. You could write plus 0 x4 if you really want to. And the third equation is 3x1 minus 2x2 plus x3 plus 2x4 equals 13. So do you see a system of 3 equations with 4 unknowns? Everybody? Okay. Now, we already know matrices. And we know how to do matrix multiplication. And in particular, we know how to multiply a matrix and a vector. So I want to show you something. I'm going to erase the top example. I'm going to rewrite this system differently. So I'm going to take a matrix in which I'm going to write just the coefficients of these 3 equations. So the matrix is going to be 1, 2, 3, 4. Those are the coefficient of the first equation. 2, negative 1, 1, and then there's a 0 here because there's no x4. And then 3, negative 2, 1, 2. So this is called the coefficient matrix. Okay. I'm going to multiply it by a column vector, a vector that has only one column, and the vector is going to be x1, x2, x3, x4. And I'm going to say this equals 13, 8, 13. These are the constants, or the free coefficients from this system. And the claim is that this product of 2 matrices giving a matrix is precisely saying the exact same thing as this. Why? Because this 13, by definition of matrix multiplication, is the first row of A times the first column of B, but B of capital B, of this matrix, right? So it's 1 times x1 plus 2 times x2 plus 3 times x3 plus 4 times x4 equals 13. That's this equation. Do you agree? Yes. And 2 times x1 minus 1 times x2 plus 1 times x3 plus 0 times x4 equals 8. That's this equation. And 3 times x1 minus 2 times x2 plus 1 times x3 plus 2 times x4 equals 13. That's this equation. So this system of equations, of linear equations, can be rewritten. This is not a new definition. It's just a different way of expressing the same thing. You may be used to this, you may have never seen this before, but it's just a different way of writing the exact same thing. Do you agree? Okay, so the coefficient matrix, let me take a different color. The coefficient matrix is usually denoted by A. So A is the, well, let's write it. I'm out of space. I'll write it in the next board. So this is A. It's called the coefficient matrix. This is X. It's called the unknown vector, the vector of the unknowns or the variables. And usually to indicate that it's a vector, we borrow notation taking from the world, the geometric world of vectors, and put a little arrow over X to indicate that it's a vector. And this equals B. B is the vector of the constants. Okay? So that's how we denote it. Okay, so compactly, any system of linear equations can be represented as AX equals B, where A is the coefficient matrix, X is the unknowns, and B is the constants. Okay, good? Okay. And the question you might ask is, what is this good for? Aha, so it's good for solving. Okay, this is gonna be the the way, or there are many ways to solving systems of equations, but the one we're going to focus on in this course is going to kind of rely on this matrix representation. Okay, and
Kramer's rule?
No guessing games. Okay, it's going to be called Gauss's method, and wait. Okay. So what I want to do, and it might be a bit scary again, but it's just intimidating at first glance, but really it's just rewriting this. I want to write all this abstractly. Okay, I want to replace 1, 2, 3, 4, etc. by A11, A12, A13. I want to write it in the abstract way. And by now I think that you already know that going to the abstract world is just a necessary step in order to carry out abstract arguments. So I don't want to just solve every system separately. I want to build a theory. I want to say how we solve it in general. Okay, and for that I have to be abstract, and then you can apply it to different examples. Okay, so here's the abstract statement. So a system of linear equations, now we're ready to write it, is something of the form A11x1 plus A12x2 plus plus A1nxn equals B1. That's the first equation. Then there's the second equation, A21x1, same variables. Okay, same variables, different coefficients, plus A22x2 plus plus A2nxn equals B2. And then and the last one is going to be AM1x1 plus AM2x2 plus plus AMNXN equals BM. Okay, so this is a system of M equations in N unknowns. Do you agree? This can be rewritten as A11, A12, A1n, A21, A22, A2n, AM1, AM2, AMN. This is, we said, called the coefficient matrix, A, which is, let's write it black. The coefficient matrix A, and then we're going to multiply it by the vector x1, x2, all the way to xn. So this is the variable, we called it x, the variable vector, and then this equals b1, b2, all the way to bm, which we denote by b, which is the constant vector, the free coefficient vector. Okay? Good. So do you see that this is just writing in using all these indices and labeling, but it's just writing that example abstractly. Okay? Okay. A bit of definitions that are going to be very useful shortly. So if all these bi's, all the b's, happen to be 0, so we're just looking at systems of equations where all the equations are of the form sum of ai xi equals 0, then it's called a homogeneous system. So if B is the 0 vector, all bi's are 0, then the system, so this is a definition, then the system is called homogeneous. And if they're not, if some of them happen to be non-zero, then it's called non-homogeneous. Okay, so if not, if B is not the 0 vector, then it is called non-homogeneous. Okay, so those are these two notions. Yeah. Okay, so the question that we want to answer now is why, so question, why write in the form AX equals B. What is it good for? Okay, and that we're going to answer, that's the question we're going to answer in the next clip.